It is the closest planet to the Sun. You would think that makes it the easiest target in the solar system. Point a rocket sunward, let gravity do the work, and coast right in. Simple. Except that in the entire history of human spaceflight, only 2 spacecraft have ever successfully visited Mercury. 2. We have sent more missions to the outer edges of the solar system, past Jupiter, past Saturn, past Neptune, than we have to the planet sitting practically in our cosmic backyard. One probe took nearly 7 years just to get there. Another is still traveling as you watch this, and it will not arrive until 2026. Mercury is close. Mercury is also, by almost every measure, one of the hardest places in the solar system to reach. And the reason why will completely change how you think about space travel. Welcome to Space Review, where we take the questions that sound simple and pull them apart until the real answer emerges. If you are not subscribed yet, now is a great time. Hit that button and the bell, and let us get into one of the most underrated puzzles in planetary science. Mercury is a world of extremes. It is the smallest planet in the solar system, only slightly larger than Earth's moon. It has almost no atmosphere to speak of. Its surface is cratered and ancient, scarred by billions of years of impacts. Temperatures swing from 430 degrees Celsius on the sunlit side to negative 180 degrees on the dark side, the single largest temperature range of any planet in our solar system. It completes one orbit around the Sun every 88 days, moving faster than any other planet. In mythology, Mercury was the swift messenger of the gods. That name turns out to be more accurate than the ancient Romans could have possibly known. And yet, for all its extremes, the thing that makes Mercury genuinely remarkable is not what it is, but how nearly impossible it is to get there. The obstacle is not distance, it is physics. And once you understand the physics, you realize that space travel is far stranger and far more counterintuitive than most people ever imagine. Here is the core paradox. To visit Mercury, you do not need more speed, you need less. And getting rid of speed in space is extraordinarily difficult. Every object orbiting the Sun moves at a speed determined by its distance from it. The closer you are to the Sun, the faster you have to travel to maintain a stable orbit. Mercury orbits at about 47 kilometers per second. Earth orbits at about 30 kilometers per second. So Mercury is actually moving faster than Earth around the Sun, not slower. When a spacecraft launches from Earth, it inherits Earth's orbital velocity of 30 kilometers per second. To fall inward toward Mercury, it needs to slow down relative to the Sun, shedding that inherited speed. But rocket fuel is heavy, and carrying enough fuel to slow down dramatically on the way in, and then slow down again to actually enter Mercury's orbit rather than just flying past it, requires an almost absurd amount of propellant. The math, known as the Tsiolkovsky rocket equation, punishes you brutally for every kilogram of extra fuel you need to carry. More fuel means more mass. More mass means you need even more fuel to move it. The equation spirals against you quickly. This is why, counterintuitively, reaching Mercury requires more energy than reaching Mars. Even though Mars is vastly farther away, Mars is beyond Earth's orbit. So a spacecraft can use the Sun's gravity to coast outward with relatively modest adjustments. Mercury is inside Earth's orbit, and getting there means fighting against the same gravitational pull that is constantly trying to accelerate you inward, making it almost impossible to slow down enough to stay. So how do you actually get to Mercury without carrying an impossible amount of fuel? The answer is a technique called a gravity assist, sometimes called a gravitational slingshot, and it is one of the most elegant pieces of physics ever applied to engineering. A gravity assist works by flying a spacecraft close to a planet or moon, and using that body's gravitational field to change the spacecraft's speed and direction without burning any fuel. The planet essentially donates some of its own orbital momentum to the spacecraft. Done correctly, A gravity assist can dramatically accelerate, or, critically for Mercury, decelerate a spacecraft relative to the Sun. The first mission to Mercury, Mariner 10, launched in 1973 and used a single gravity assist around Venus to redirect itself toward Mercury. It flew past Mercury 3 times between 1974 and 1975, but never entered orbit. It was moving too fast to be captured by Mercury's weak gravity, so it just kept passing through. The second mission, Messenger, launched in 2004, was the first spacecraft ever to orbit Mercury. But getting into that orbit required one of the most complex trajectories ever designed for a planetary mission. Messenger performed 6 gravity assists in total, 1 around Earth, 2 around Venus, and 3 around Mercury itself, each time bleeding off a little more of its excess velocity, before finally slowing down enough to be captured into Mercury's orbit in 2011. The entire journey took nearly 7 years. 7 years to reach the planet closest to the Sun. And Messenger still needed a massive fuel burn, the largest rocket engine firing of the mission, just to enter orbit. Even after all those gravity assists, the spacecraft was still moving fast enough that without that burn, it would have sailed right past Mercury and been lost. Speed is not the only enemy. Heat is too. Mercury sits so close to the Sun that solar radiation there is between 5 and 10 times more intense than what Earth experiences. Any spacecraft visiting Mercury has to survive that continuous blast of energy while simultaneously keeping its instruments cold enough to function correctly. Messenger solved this with a sunshade, a ceramic fabric shield about the size of a large door that was always kept pointed toward the Sun. As long as that shade was properly oriented, the instruments behind it stayed at manageable temperatures, but it required the spacecraft's navigation systems to maintain precise pointing at all times. Any serious misalignment, and the electronics would begin to cook. The surface of Mercury itself presents additional challenges for any future lander. The temperature swings between day and night are so extreme that materials expand and contract in ways that can fracture hardware. The near-total absence of an atmosphere means there is no cushion for a landing, no parachutes, nothing to slow a descent. Any lander would need to use rocket engines to touch down, which adds yet more fuel to an already fuel-hungry mission. Despite how difficult Mercury is to reach, the missions that did get there returned genuinely stunning science. Messenger revealed that Mercury has a surprisingly large iron core, taking up about 85% of the planet's radius. For comparison, Earth's core takes up roughly 55% of our planet's radius. Scientists are still debating why Mercury's core is so disproportionately enormous. One leading theory suggests that a massive collision early in the solar system's history stripped away much of Mercury's outer rocky mantle, leaving behind an unusually dense, iron-rich world. Messenger also discovered something that shocked almost everyone: water ice. At the poles of Mercury, inside permanently shadowed craters that never receive direct sunlight, temperatures are cold enough to preserve ice. On the planet closest to the Sun, just a few degrees from regions hot enough to melt lead, there is frozen water. It was not there from the beginning. Most scientists believe it was delivered by comets and asteroids, impacting Mercury over billions of years, the same process thought to have brought water to early Earth. Mercury also has a magnetic field, which was unexpected for such a small, slowly rotating world. Earth's magnetic field comes from its churning liquid iron core, but Mercury rotates so slowly that scientists did not expect it to generate a significant field. Yet it does, albeit far weaker than Earth's. Understanding why continues to challenge planetary scientists. Right now, a spacecraft is on its way to Mercury, and it is the most sophisticated probe ever sent there. BepiColombo is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, launched in October 2018. Like Messenger before it, BepiColombo cannot simply fly straight to Mercury. It is executing a series of 9 gravity assists across Venus and Mercury itself before it will be slow enough to enter orbit in late 2026. During its long journey, BepiColombo has already returned new data. It has performed close flybys of Mercury and captured detailed images of the surface, revealing geological features that Messenger's instruments could not fully resolve. Scientists are particularly excited about BepiColombo's ability to study Mercury's magnetic field with far greater precision than any previous mission, which could finally clarify why such a small planet generates a magnetic field at all. BepiColombo is actually 2 orbiters traveling together and then separating once they reach Mercury, one European and one Japanese, each designed to study different aspects of the planet simultaneously. This paired approach has never been attempted at Mercury before, and it should yield more comprehensive data than any single spacecraft could gather alone. The mission also carries instruments designed to study the tenuous exosphere surrounding Mercury, the wispy near vacuum that functions as a stand-in for a real atmosphere. Understanding how that exosphere is generated and maintained by solar radiation and meteorite impacts will give scientists new insight into how airless rocky bodies interact with their stellar environments, which has implications for understanding planets far beyond our own solar system. Mercury is not just scientifically interesting in its own right. It is a window into the early solar system. Because it has almost no geological activity and no weather to erode its surface, Mercury is essentially a time capsule. Its craters and terrain have been largely unchanged for billions of years. Studying them is like reading the first pages of the solar system's history. Understanding Mercury's outsized iron core also has implications for our models of planetary formation. If a large impact really did strip away much of Mercury's outer layers, then similar violent collisions may have been common across young planetary systems elsewhere in the galaxy, fundamentally shaping the kinds of worlds that form around other stars. There is also a longer-term question about Mercury's resources. Its polar ice deposits, shielded from the sun in permanently shadowed craters, represent water in an otherwise scorched environment. Some researchers have speculated about the theoretical possibility of robotic operations at the poles one day. The engineering challenges are immense, but the presence of water anywhere in the solar system tends to attract serious attention. More practically, every mission to Mercury teaches engineers and mission planners lessons that transfer directly to future deep space exploration. The gravity assist techniques refined on Messenger and BepiColombo are the same fundamental tools that will be needed for missions to the inner solar system and beyond. Mercury is a training ground as much as it is a destination. Mercury is not hard to visit because it is far away. It is hard to visit because of a beautiful and brutal piece of physics that punishes any spacecraft trying to slow down inside Earth's orbit. It is hard to visit because the sun's radiation makes the environment nearly lethal to delicate instruments. It is hard to visit because its tiny gravity provides almost nothing to help a spacecraft break into orbit. Every mission to Mercury is an exercise in patience, precision, and engineering creativity stretched to its limits. And yet, the 2 missions that made it there changed everything we thought we knew about this small, scorched world. Water ice at the poles of the hottest planet, a core that makes no sense under our original models, a magnetic field that should not exist. Mercury keeps defying expectations, and BepiColombo has not even arrived yet. The closest planet to the Sun remains one of the least understood worlds in our solar system, and the harder something is to reach, the more it tends to be worth the journey. If Mercury just became a lot more interesting to you, you are not alone. Drop a comment below and tell us what surprised you most: the ice at the poles, the giant iron core, or the 7 years it took just to get into orbit. Share this with someone who thinks space travel is just pointing a rocket and going. And subscribe to Space Review, because next time we are diving into something that scientists have been quietly debating for years, and the answer is not what most people expect.